So, hello everyone, I'm Sachin, and let's continue our series on density operators, third order nonlinear response theory, and so on and so forth. So, with special emphasis towards spectroscopy. So, in spectroscopy, we calculate polarizations, and we had calculated the third order polarization in the previous class, where assuming you have some sort of sample and you have three light fields which are incident on your sample, and then the signal which is recorded is your third order macroscopic polarization. So I did not use the word macroscopic in the previous class, but it is implicitly assumed that polarization is a macroscopic quantity and not a microscopic quantity. Yes. So this is the signal which we are looking to calculate, and we had attempted to calculate the signal in the previous class, and the way we calculated it was by taking the trace of the dipole operator with the third order density operator term. So this is how we calculated it in the previous class, and we got the following result where we ended the previous class. So you have a triple integral over the three delays T1, T2, and T3. You have three electric fields, which are scalar electric fields here. Just a reminder, we have ignored the vectorial component of the electric fields and the transition dipole operators as of now. And along with it was our measured response function. So this response function, we call it R henceforth, and is a function of the three delays. And then this response function took on the following structure, which we had derived, and is as follows, is given by the trace of the dipole operator at T1 plus T2 plus T3 along with the commutator or nested commutator, which contains three dipole operators, which are at times T2 plus T1, T1, and 0. And you have your equilibrium density operator, which we are denoting by rho 0. So this is our equilibrium density operator, and these are essentially your dipole operators which bring about transitions in your system which is being probed. And then this dipole operator, as I had previously described, is the one corresponding to the emitted field. Yes. So this was our third order nonlinear response function, and people often put a 3 on top to represent it, but we needn't do that because it is explicit that we are not measuring any other orders, so we will not do that. So now, what do we need to do to proceed? Before I proceed, I would like to mention that this response function, R3, T1, T2, T3, is dependent only on the matter system henceforth. So the entire idea behind the expression which we have calculated here for the third order polarization is that you have these three electric fields which are representative of the perturbations, and then we have this response function. So this response function only depends on the matter Hamiltonian, to be more precise. So when you think about its mathematical structure too, these dipole operators in the interaction picture are a function of h0, where some u hat t is given by e raised to the power I h0 t upon h bar u hat and e raised to the power minus I h0 t upon h bar. So this is the dipole operator in the interaction picture, which we had covered in the previous class. And you can observe that the entire mathematical structure of the response function depends only on H0 operator. So it does not depend on the perturbation V. So I should have been more clear with that. So this is independent in the independent of V. So we have taken care of the perturbation now, and the remaining response function is just dependent on the matter system. So before I proceed, I would like to clarify that this matter system is everything that is contained within your sample cuvette which is being probed. So that would in general consist of three components defined under something which is known as a system bath picture, where you have some system Hamiltonian, bath Hamiltonian, and some interaction between the system and bath. So, one simple example would be to consider electronic spectroscopy, where let's just say you have some chromophore. Let me call this an chromophore, which absorbs UV or visible light, let's just say. So it's electronic spectroscopy, and it interacts with its surrounding solvent molecules. So this interaction between your system and surrounding solvent would classify as a system bath interaction, and then the bath would be the surrounding solvent, and then the system would be the chromophore. So here we need to clarify the nomenclature very clearly. So if you have a specific spectroscopic technique, so the system only comprises of the degrees of freedom being directly probed by the spectroscopic technique. So what does this mean? What this means is that, let's just say I'm doing an electronic spectroscopy experiment. My system will only include my chromophore, and more specifically, the electronic degrees of freedom of my chromophore. They will not include any other degree of freedom. So let's just say my vibrational modes of my chromophore will also be treated as my bath. So that's something to be very carefully taken care of. So let's just say I'm doing vibrational spectroscopy. Okay, so I should mention that degrees of freedom. So I would mention relevant here. So it only includes the relevant degrees of freedom being probed by the specific spectroscopic technique. So let's just say I'm doing vibrational spectroscopy and I have a specific vibrational transition. And this is the only specific transition which I want to look at. So this would constitute my system. And let's just say I have other vibrational modes interacting with this system and perturbing this system. So let me just mention perturbed by other vibrational modes, let's say. In this case, the other vibrational modes will be treated as a bath. So, to be very specific here, so the system only includes the relevant degrees of freedom, which I want to probe in the specific, which I want to probe using the specific spectroscopic technique. And my bath includes everything which is not my system. So that includes other vibrational modes and can include, if it's a solid state sample, it can include your phonon modes and can also include overdamped solvent contributions. So everything other than the system is the bath. So this is the model. But I would like to make very clear right now, since we have only began studying spectroscopy, and this is an introductory multidimensional spectroscopy class, I will restrict my Hamiltonian, my matter Hamiltonian, to only consider my system Hamiltonian. So, what that means is later on, we will incorporate the bath, and as a consequence, you will have some system bath interaction. So, these components will be introduced later on into our formalism. So, let me repeat, as of now, in our formalism, we are restricting the matter system to the system Hamiltonian. So the system Hamiltonian will only contain the energies of the relevant degrees of freedom which you want to probe in your specific experiment. So let me give you a specific example of what we are going to do. So consider an electronic spectroscopy experiment in this case, described by some ground electronic state G and excited electronic state E. In this case, your system will not be interacting with any external environment. So the way I would describe this is that this is an isolated system. So this two-level system in my thought experiment is an isolated system. So in our initial simple description, we will consider isolated systems where the Hamiltonian is restricted purely to the system Hamiltonian. And in this case of this two-level system, I would describe my system Hamiltonian very simply as the energy of the ground state and the energy of the excited state with no off diagonal terms. So this would be my system Hamiltonian in a very simple case. And there's no bath contributions or system bath interactions in our current formalism. We will introduce the system bath and the bath Hamiltonians later on because this system bath coupling is critical in describing spectroscopic line shapes. So this system bath interaction is what governs the line shapes of your spectrum, either in linear absorption spectroscopy or in multidimensional spectroscopy. So they are very critical and need to be studied later on. But as of now, to get an idea of how your third order nonlinear optical response function looks like, so to initially study its mathematical structure, we make the approximation that the Hamiltonian, your matter Hamiltonian or your matter system just contains your system Hamiltonian. So let us return to the structure of your response function and expand the nested commutator within the response function structure. By expanding the commutator within the response function structure, we will get insight into the signals which are generated as a consequence of your three light fields. So let me rewrite the response function structure. Oh, before I proceed, I would like to mention that in the last class, we had not discussed the impulsive limit approximation, where I had just left off by mentioning that these electric fields will be treated like delta functions. So the way we treat this triple integral and these electric fields, we will come back to it once we describe the third order nonlinear response function which is this, which I'm going to write down the mathematical structure of. So once we describe this mathematical structure and study various signals corresponding to simple systems, we will come back and discuss the electric fields, which will play a key role in describing the direction along which the signals will propagate. So, from this response function expression, which I have here, you will generate various signals, or you will be able to study the various signals which are generated as a consequence of your light fields. But to understand in which direction these signals propagate, and we will have to introduce some other approximations as well. We will have to return back to the electric fields. So we will return back to the electric fields in a while. So as of now, let's just stick to evaluating the structure of this response function. So it's given by the trace of mu t3 plus t2 plus t1, and along with the commutator, the nested commutator, which we will be expanding soon. So this is what you get, and this is your equilibrium density operator. So let us start by expanding this nested commutator. So we will do it stepwise. Let us consider the innermost commutator first. So the innermost commutator will just give you mu 0, rho 0, minus rho 0, mu 0. So we will evaluate this stepwise so that everyone is clear with this evaluation, because the expansion of this nested commutator will give us 8 terms, and each of these 8 terms will have to be multiplied with this. So you have to be very careful while evaluating this nested commutator. So we will go through it step by step. So the first commutator will give you 2 terms, and then this resultant term will have to be commuted with mu t1. So that would give you 4 terms. So let us evaluate that. So you have mu t1 along with these 2 terms, along with these 2 terms, and along with it, you will have the second term, which is given by this, along with mu t1. So this is what you get after your second evaluation. And finally, you will have to commute this expression with mu t2 plus t1. But before I do that, I will have to do an expansion of this. Otherwise, it would get confusing. Mu t1, mu 0, rho 0, minus mu t1, rho 0, mu 0, minus u0, rho 0, mu t1, plus rho 0, mu 0, mu t1. Now I will commute this with, let me choose another color, with mu t1, sorry, not with mu t1, with mu t2 plus t1. We have already commuted with mu t1. So what that will give us is 8 terms, and those 8 terms will have to be multiplied with mu t3 plus t2 plus t1, which is given here. So I'm going to jump the gun a little bit and write down all the 8 terms multiplied with mu t3 plus t2 plus t1. So what will that give us? You have mu t3 plus t2 plus t1 times mu t2 plus t1, mu t1, mu 0, rho 0. So this will be your first term which we get after all of this expansion. Then you get mu t3 plus t2 plus t1 times mu t2 plus t1, mu t1, rho 0, mu 0, and then after that you will get mu t3 plus t2 plus t1, mu t2 plus t1, mu 0, rho 0, mu t1, and then you get another positive term, mu t3 plus t2 plus t1, mu t2 plus t1, rho 0, mu 0, and then mu t1. So these are our first four terms, and then you will have the other four terms with a negative sign. So you get mu t3 plus t2 plus t1, mu t1, mu 0, rho 0, and then the mu t2 plus t1 will act from the right side in this case. So then you get mu t3 plus t2 plus t1, mu t2 plus t1, mu, I'm sorry, this will not come here, it will come on the other side, mu t1, rho 0, mu 0, and then mu t2 plus t1. Then you get another positive, mu t3 plus t2 plus t1, mu 0, rho 0, mu t1, and then mu t2 plus t1 acting from the right hand side. And after this laborious exercise, we have just one last term left, which is mu t3 plus t2 plus t1, rho 0, and then you have three operators acting from the right, which is mu 0, mu t1, and mu t2 plus t1. So this is what you get in the end after expanding your commutator out. Now note that I have to still take a trace of all of this. So my resultant expression will just be a trace of all of these quantities. So now I would like to recall a specific property of the trace which I hadn't gone over but is quite simple and easy to understand, that the trace is additive. So the trace of A plus B plus C is just equal to the trace of A plus the trace of B plus the trace of C. So this is a property of the trace. So what I'm going to do is these 8 terms which I have just derived by expanding the structure of the nested commutator, I can split these terms into 8 individual terms. So that is what I'm going to do. I'm going to lay down a specific strategy here. One, which would be to split into 8 individual terms. And number 2 would be I will use the cyclic property of the trace, which is the trace of A hat, B hat, C hat will be equal to the trace of C hat, A hat, B hat, which we have proved in the density operator 1 lecture. And what will end up happening is I want all these terms with rho 0 all the way to the right. So there are 4 operators which are acting on this equilibrium density operator given by rho 0. And I want rho 0 to be at the utmost right, and the 4 operators to act from the left on rho 0. So I will move this mu 0 here. I will move this mu t1 here. I'll move this mu t1, mu 0 here. And likewise, I would perform that operation for all these 8 terms. So I'm going to do these two things. And the reason behind performing the second step is very evident, that if you have, let's just say, the trace of an operator A, B, and C acting on, let's just say, your equilibrium density operator, as is the case above, where you have these dipole operators in the interaction picture, hence the time dependence of the dipole operators. and these act on your equilibrium density operator above. So if you recall that the trace of, let's just say, any operator, so the product of these operators will effectively give you another operator, right? So the trace of this operator, let me call it D, which is the effective operator of constructed from actually sitting and multiplying the three operators, is just given by the expectation or the expectation value of the operator D. This is something which we have described very clearly in the past, that let's just say you have some observable A. Let's just be more generic and mention that this observable has some time dependence. So the expectation of this observable is calculated by taking the trace of this observable with the with the density operator at time t, and this is equivalent to taking the trace of the observable at time t and keeping the quantum system at rest. So this is what we want to do. So in principle, we should also highlight what we have done from a broad scope, because doing the math is simple, but understanding why we are doing the math is rather complicated. So I would like to take a moment before I continue evaluating the response function structure to describe why we have done this. So for that, let's go back to the beginning of our derivation, which starts with the third order polarization, or in general, let's forget about the third order term and consider the polarization of a matter system in general, denoted by P of t. And we denoted it as the expectation of the dipole operator. So the polarization in any system can be calculated by computing the expectation of the dipole operator. Or to be more concise, it would be the expectation of the dipole operator at time t, because we are measuring the polarization at time t. So the way we can compute this is two ways. There's two ways to compute it. One would be to take the trace of the dipole operator at rest with the evolved density operator, or equivalently take the trace of the dipole operator evolved to time t with the equilibrium density operator, or rho 0. So what we started off with was calculating the third order polarization by taking a trace of the dipole operator at rest with the third order density operator term, which is evolved in time. So now I would like you guys to think about a more physical picture. Let's just say you have some system which you're probing, and you have three light fields which probe these system. After a specific light field, let's just say the first light field is incident on the system goes from being in equilibrium. So before the light fields are incident on the sample, the system is in thermal equilibrium, or is assumed to be in thermal equilibrium. And once the first light field is incident on the sample itself, it goes to a non-equilibrium state. So these light fields which are incident on your sample take your sample from an equilibrium state to a non-equilibrium state. And this non-equilibrium dynamics is exactly what you're trying to probe. So this non-equilibrium state which evolves in time is exactly what is given by the rho third order density operator term. So this describes your non equilibrium system evolving in time. To be more precise, which is not necessary at this stage, if you remember your third order dipole operator, let's just say I pull out some time evolution operators to describe this to you, would be I pull out my evolution with respect to the matter system. So I get this third order dipole operator in the interaction picture, which we have talked about in the previous lecture. So I'm just doing something from the previous lecture. This rho IT third order is what actually, to be more precise, describes the non-equilibrium system. So the non-equilibrium system is that which is described by the evolution of the equilibrium system with respect to the perturbations, which is this rho 3 IT. So this describes your non-equilibrium system. So your system, so what does this quantity mean in the end? So it means taking the expectation of mu over a non-equilibrium system. What does this mean? It's a non-equilibrium statistical average. So it's a non-equilibrium ensemble average. So this is what we started off with. We started off with taking a non-equilibrium ensemble average. And where are we left off now? Now we are measuring the polarization as various quantities which are equilibrium averages. Now, what does this mean? If you go back up, as I had just described, what I'm going to do now is to move these dipole operators such that they act from the left, and to the right would be my equilibrium density operator. And then the trace of these dipole operators, which are evolving in time, are taken with the equilibrium density operator. So that's why I'm saying equilibrium ensemble averages. So now what I am doing in this case is, let me just write down one of these 8 terms from the top, where you have, let's just say, mu hat T3 plus T2 plus T1, mu hat T2 plus T1, mu hat T1, mu hat 0, rho 0. This is one of the terms there, and it is a trace. So this is how this term looks like. And this term will just be equivalent to measuring the expectation of this effective observable. And it is an equilibrium average because my density operator is at rest. So this is just mu hat T3 plus T2 plus T1, mu hat T2 plus T1, mu hat T1, mu hat 0, and this is an equilibrium average. So, in short, if you haven't really gotten the description of what I'm trying to say, it is that we have gone from taking a non equilibrium average of the static dipole operator to taking an equilibrium average of the evolving dipole operator. And this is a theory in statistical mechanics which is very well known, that taking an equilibrium average of evolving observables is equivalent to taking a non-equilibrium average of a static observable. And I suppose I have made this very clear, but I have described this in previous lectures too, where in one case you are evolving the system and in another case you are evolving the observable. So the physical interpretation is well described now. So that's what I want to do as well. So I want to rewrite these 8 terms as equilibrium averages by moving the dipole operators to all act from the left, and the trace of these effective operators acting on your equilibrium density operator is just the equilibrium average of the observables. So by doing so, by following step 1 and step 2, the math reduces down as follows. So the third order nonlinear optical response function can now be written as just we're going to drop this out soon as I previously described. Another word of caution, I'm going to be reorienting the terms in my current description, so I'm not going to be putting this term at the top, and I will explain the reorientation to you guys in a little while. And using the I'm describing this for the 50th time, just using these two properties or tricks which I have described, I will be rewriting the expression, which is equal to I upon h bar cube. Let's not forget this factor times the 8 terms, which are. I will explain to you why. Let me start writing the terms as the first term and then the second term. So I apologize if I've been inconsistent in my notation, where at some places I have been using T3 plus T2 plus T1, and in some places I have been using the other convention. So I'm going to stick to the one where I mentioned the earlier times first, but of course, that doesn't make a difference. But I will mention it this way from now. And then you have 0. These are equilibrium averages, but I will not mention this after this. It is assumed to be an equilibrium average. And so I'm just rewriting the 8 terms, and we will start labeling these individual response functions. So this is the complete response function, and within the complete response functions are, you can call them so-called mini response functions, or the signals, the individual contributions towards the complete response function. But if this and this are individual response functions, we will call them R1. And some people, as usual, put a 3 on top, which is the same 3 here to note that it's a third order nonlinear response. But yep, and it's a function of T1, T2, and T3. And then I would call this R2, T1, T2, and as a function of T1, T2, and T3. And likewise, I will have to write 6 more terms, and the reasoning behind their labeling and the way they are oriented will be understood shortly. So this is going to be called R3, and then correspondingly we have an R4, and these are the 4 terms with a positive sign before the commutator. I have changed the convention again, so let me stick to what I promised. Okay, so this is R4, and these are the 4 positive terms. And the remaining 4 negative terms are just going to be R1 star, R2 star, R3 star, and R4 star. I will write them down, and it will become quite obvious to you once I write these terms down, oh no, t1 plus t2 plus t3 mu t1 plus t2 and then mu t1, and then this would be r1 star. And this can easily be verified. Since this is an expectation value, it corresponds to some scalar as such, and then what you could do is just take the complex conjugate of this expectation value, and when you take the complex conjugate, just know that these are observables or operators. So when you do that, when you have observables or operators, you need to take a Hermitian conjugate of each. And the Hermitian conjugate of, let's just say, a bunch of operators would be the Hermitian conjugate of each individual operator, but the order is reversed. So this would come first, then this, and then this. And just know that the dipole operator corresponds to a physical observable. So the Hermitian conjugate of the dipole operator would just be itself. So what you just need to do is invert the order. So there would be mu t1 first, then mu t1 plus t2, then mu t1 plus t2 plus t3, and then mu 0, which is exactly identical to this. So this is just r1 star. And likewise, we will have three more terms with the same complex conjugate, where it can be observed now that this is just a complex conjugate of R2. I'm going to not write the T1, T2, and T3. It's well known that they are functions of T1, T2, and T3. So this is just the complex conjugate of R2 star. Then you have the complex conjugate of R3 star, and likewise you have the complex conjugate of R4 star. And maybe I should skip this to save some time. And the complex conjugate. So it is very clear here that you have four terms and their corresponding complex conjugates. So your, I'm not going to write the three from now. So your response function is of the following mathematical structure, where you have n going from 1 to 4, and then you have Rn t1, t2, t3 minus Rn star t1, t2, and t3, where R corresponds to your response functions. So now what we could do is evaluate these R1, R2, R3, and R4 to find out what the response is. But before we go ahead and do that, let's get some physical understanding on what is going on. So to get some physical understanding on what is going on, we have to look at each individual expression, R1, R2, R3, and R4. And then we, for now, will not consider R1 star, R2 star, R3 star, and R4 star on grounds that the physical understanding or the physical intuition which I'm going to provide is for a simple two-level system or TLS. So I'm only going to have a ground state and an excited electronic state. So if I have a ground state and an excited electronic state, this is some sort of statement which I'm making right now, but it will be clear to you guys why this is true, you just need R1, R2, R3, and R4, and the corresponding complex conjugates can be taken care of as I will show below. Because if you have some term minus its complex conjugate, you are just referring to the imaginary component of that term. But this assumption, I mean, not this assumption, but this assertion is only true for a two-level system. And the reason behind that is that there are other signal contributions to these complex conjugates when we divert away from a simple two-level system. So, but for a simple two-level system, these can just be assumed. These are just the complex conjugates of the first four terms, and hence the signal which you get or your response function here is just directly proportional to the imaginary part of these individual Rn. Okay, so to get a physical interpretation, let's just consider R1, R2, R3, and R4. So let us start off with R1. By the way, I would like to inform that these terms here are known as 4-point dipole correlation functions. They're known as 4-point dipole correlation functions. 4-point because there's four dipoles, and then dipole, of course, because it's a correlation of where the four dipoles. So that's why it's known as a 4-point dipole correlation function. So let's consider our first 4-point dipole correlation function, or the sub response function R1. So if I consider response function R1, I have the following structure. Mu hat T1, mu hat T1 plus T2, mu hat T1 plus T2 plus T3, and mu hat 0. I do not know if you recall this, but as I had mentioned in the previous lecture and at the beginning of this lecture, that the fourth dipole operator corresponds to the emission of the signal field. So this guy here corresponds to the emission of the signal field, whereas these three dipole operators contribute towards the evolution of the system and uh, the various transitions which take place before the emission of the signal field. So this is kind of backtracking, but I would have to go back to the previous trace notation. So the expectation of an observable is given by the trace of that observable with the equilibrium density operator. So you might be wondering why I have derived these expressions if I'm going from these expressions back to these expressions, but just a word of caution that these expressions are very good in deriving the final analytical expressions. So I wanted to progress in this direction, and I wanted to give you guys a good intuition on non-equilibrium and equilibrium averages. That's why I took the next step here, but I would have to backtrack one step right now. So I will be backtracking one step, and yes, I will be taking the trace of these four dipole operators with the equilibrium density operator. So you have this mu hat T1, mu hat T1 plus T2, mu hat T1 plus T2 plus T3, mu hat 0, and rho 0, which to remind you is the equilibrium density operator. So what you would want to do now is to think about the invariance of the trace to cyclic permutations, and when you do that, you get this expression mu hat t3, t1 plus t2 plus t3 mu hat 0 rho 0 mu hat t1 and mu hat T1 plus T2. If you're currently confused about how I went from here to here, what you could do is you can backtrack. So you can look at the final expression and see that if the trace is invariant to cyclic permutations, this will come here, and then after that, this will come here. So you get mu T1 plus T2, and so both these expressions are equivalent because of the cyclic property of the trace. So now that these expressions are well ordered in time, you can understand this. So, and then this interpretation part is very interesting. So you have the ground dipole operator or the equilibrium dipole operator. So assuming that the equilibrium dipole operator is confined to one specific element in the matrix. So this is a 2 by 2 matrix in the consideration of a two-level system. And it is equal to 1, 0, 0, 0. And this, as I had previously told you in the previous class, the diagonal elements of the dipole operator correspond, or in this case, in this matrix representation, correspond to populations. So this corresponds to the population of the ground state, and this corresponds to the population of the excited state. And of course, there are no coherences or coherent states before any light field is incident on the sample. So this means that the probability of finding your sample in the ground state before any light field is incident on it is equal to 1. Note, very important, this is only valid for electronic systems or vibrational systems with a very large energy gap, or with omega nu being large. The reason behind this is that the probability of your system being in the excited state scales with the Boltzmann's factor, which is given by exponential minus delta Eg over the Boltzmann constant times temperature. So if this delta Eg in the case of an electronic system is very large, then obviously you will not see any excited state population. So this would be in 10,000 to, let's just say, 20,000 wave numbers. So it's tens of thousands of wave numbers. And this is about 206 wave numbers. So you can already see how small the probability of being in the excited electronic state will be if it is an electronic transition. But if you're considering vibrational transitions, where let's just say the vibrational split is like, in a very rare case, let's just say like 2000 wave numbers, and this 206 wave numbers is at room temperature. Let's just say you're running your experiment at, let's hypothetical 100 Kelvin. Okay, not hypothetical. Hypothetical would be 0 Kelvin. Let's just say you're running it at 100 Kelvin. So this factor would also be much smaller. And then in that sort of scenario, you could probably then ignore the excited state populations. But this approximation is mainly valid for electronic spectroscopy. So my equilibrium density operator would just be G, G. You just have one element. So what happens is you are probing your equilibrium density operator. Now, the first light field at t equal to 0 interacts with the ket side. So this is GG. And you have a ket side and then a bra side to each element of your density matrix, or yeah, density matrix or density operator. And that's how the density operator is defined. It is the outer product of a state vector in the Hilbert space with itself. So all the elements of the density operator will have the same structure, right? So, and then this mu zero is essentially the transition dipole operator, which acts on the ket side of the equilibrium density operator. So how would I think of it? I will start constructing a diagram, and then this diagram will be clear soon. So I'm initially in the ground state of the equilibrium density operator, and at t equal to 0. So this is t equal to 0. I have a light field which interacts with the ket side of the density operator through the transition dipole operator and causes a transition from the ground state to the excited electronic state. As of now, I have not defined the structure of this dipole operator, the mathematical structure, but I will define its mathematical structure when we start evaluating the exact analytical expressions from this point forward. But for now, let's just consider that this dipole operator brings a transition from the ground state to the excited electronic state. And this is from the ket side. So we go from GG to EG. Right. And then your system evolves in this coherent state over T1. So what this essentially means is that there is some transfer of population from your ground state to your coherent state, and your system evolves in the coherent state over T1. So there is some coherent state population, or I wouldn't say population, but the system is in a superposition state over T1. Then what happens is that your second light field is incident on the sample after T1 evolves, and that acts from the bra side. So it acts from the left hand side. And when it acts from the left hand side, it excites the system, the bra G, which is given here, to bra E. So after that, you reach a population state. So essentially, your population, which is initially in the ground electronic state, has gone to this coherent state, and from there, it is moving to this excited electronic state. So over T2, there's no off diagonal population. So this population which initially exists over T1 vanishes, and then you only have diagonal terms over T2. Of course, this is the very simple vanilla example. You could be in coherent states over T2 too, and they could be population coherences and this and that. So you shouldn't be worrying about those right now. As of now, you would be in an excited electronic state over T2. So there is some population from the ground state, and after interaction with the two light fields, we have gone to the excited electronic state, as is shown here by this diagonal density operator term. After this, after the evolution in the excited population state over T2, the third dipole operator acts on your density operator. So the third dipole operator again acts from the bra side at T1 plus T2. And now, since you're already in an excited electronic state and it's a two-level system, this dipole operator can only be emitting some light. So this emission is shown by this outward arrow, and it brings your system back into a coherent state. So you go back to EG. And now you have to go back to your expression And then the last dipole operator, which is the emission of your signal field, and I have repeated this so many times, acts from the ket side. So what happens here is that the emission of the signal field is generally shown using dashed arrows. The reason behind showing it using dashed arrows is that it's the emission of the signal field and it's different from the other interactions. And after evolution of the coherence over T3, the signal field is emitted and you go back to the ground state. So the entire idea is that you start off at the ground state. Your first light field interacts with the ground state. You're in a coherent state or a superposition of the ground state and the excited state. And then you have the second light field which interacts with the bra side of this coherence and takes you to a population state. After the evolution of your population over T2, you have the third light field which is incident on the sample, and then that causes your population state to go back to a coherent state. And then after the evolution of this coherence over T3, there's the emission of the signal field and you go back to the ground state. So these diagrams are known as double-sided Feynman diagrams, or in short, DSFTs. This is a double-sided Feynman diagram, so DSFT. They're alternatively also called coherence transfer pathways, and the name is quite easy to understand and infer from the diagram that there is a transfer of coherence. So it is known as a coherence transfer pathway, like how I described to you previously. In the ground state, then a coherent state, then a population state, then a coherent state, and then back to the ground state. So this population being transferred from the ground state to the excited state takes place through coherent mechanisms, or mechanisms in which your population is in a superposition of the ground and excited state over your T1 and T3, and hence they're known as coherence transfer pathways. Now, these terms T1, T2, and T3, as I had previously described to you, are just the waiting times between the fields, and they have some special names. So T1 is the waiting time between the first two pump pulses. So if, let's say, this is time 0, and then this is your first pump pulse, and then after some arbitrary time t1 you have your second pump pulse. They're generally identical, excuse my drawing. And then after some time t2 you have your probe pulse, and then after some time t3 you have the emission of your signal field. Right, so this t1 is the time during which your population is in a coherent state or in a superposition of the ground and excited electronic state, and is hence known as the first coherence period. This T2 time is known as the population time or the waiting time. The term population time is very easy to understand because you are in a population state during that time. And waiting time, it's because if you have systems which are not just two-level systems, during this period of time, you can see energy transfers from one excited electronic state to the other, and then you see various system bath interactions and so on and so forth. Even for simple two-level systems, you see system bath interactions and something which is known as spectral diffusion in multidimensional electronic spectroscopy, specifically 2D spectroscopy. So when you see those things, it's like it's a function of the waiting time T2. And then this T3, as you can already infer by now, is just your second coherence period. Right, so this is R1, and R1 stands for your this is a new term, non-rephasing stimulated emission process. So it's quite easy to understand why it is a stimulated emission process, because Before the first light field, you're in the ground state, and then the first two light fields which are incident on your sample take you to an excited electronic state. So you're in an excited electronic state over T2, and then the probe pulse or the third pulse takes you from an excited electronic state back to the ground state. Actually takes you to a coherent state, but this is an emission process. So the third light field causes or stimulates an emission of, generally people would use the word photon, right? So this is a stimulated emission process. The word non-rephasing is not too trivial to understand at this point, but since the coherences over T1 and T3 uh, oscillate in a similar fashion. If you're confused by the oscillation, don't worry about it. We will think about it later on. But if you are familiar with coherences and know that coherent states oscillate over the particular periods over which they exist, the oscillation of both of these coherences will be identical. And as a consequence of which, the phase which the first oscillation acquires is just added on to by the second oscillation. So their phases just sum up instead of canceling each other. So that's why they do not regain their original phase and hence is known as non-rephasing. So if the word non-rephasing is not clear yet, please don't worry about it. We will come back to it later on. Likewise, for the R2 process, which is mentioned here, you can construct a response function, and likewise for R3 and R4. Now, I would leave this as an exercise to you guys, but I would like to highlight that it's extremely important to think about it. So, what you have to do is construct homework, I would say, construct the double-sided Feynman diagrams for R2, R3, and R4. So what you have to do to do this is follow the same procedure as I have. Take the 4-point dipole correlation functions for R2, R3, and R4, following which rewrite them again in the trace format with the equilibrium density operator and arrange them in time neatly around the equilibrium density operator and then study their interactions. So R2 should correspond to something which is known as a rephasing stimulated emission for the two-level system. R3 should correspond to a rephasing ground state bleach, and R4 should correspond to a non-rephasing ground state bleach. We will construct these Feynman diagrams in the next class, and we will proceed to evaluate analytical expressions for these four response function expressions for the simple two-level system, assuming a simple matter Hamiltonian, which consists only of the system and does not contain any path interactions which contribute mainly to the spectral line shape of your spectra, as is very important, but for now, we are restricting our discussion just to understanding the basic mathematical structure of these response functions. So we will continue in the next class.